In this session, we're going to be looking at one of the most important concepts in programming, and that's recursion. Ever since you were probably little, you were taught using an iterative approach, where you perhaps increment a loop counter. Recursion works slightly differently. It's the ability of a procedure or a function to call itself. So in essence, you are not just getting the results straight away. The results or the answer depends on the answer of another calculation. So the joke kind of goes like this. To understand recursion, one must first understand recursion. And if you understand how that joke works, you already know what recursion is. And if you don't, it'll all make sense by the end of this session. Not only have you got to show an understanding of the essential features of recursion, you also got to show an awareness of what a compiler has to do to implement recursion in a programming language. So we're going to be looking at both of these today. A recursive routine is a function or a procedure that's defined in terms of itself. What do we mean by that? Well, think about this. If you know a bit of mathematics, you know that there's something in maths called factorial. And let's just start with something easy. Find the factorial of 3. The mathematical symbol for factorial is the exclamation mark. And what that basically means that to work out factorial 3, you've got to work out the factorial of 2. And then to work out factorial of 2, you have to work out the factorial of 1. The actual calculation works like this. Factorial of 3 is equal to 3 times factorial of 2. And factorial of 2 is 2 times factorial of 1. And factorial of 1 is 1 times factorial of 0. And it doesn't matter whether it's 3 or it's 3000, the steps are going to be exactly the same. So we can probably write a function that can work all of this out. And you see an example on screen. The function factorial takes an integer n, and n could be 3 or 3000, that's up to us, and it returns an integer value back to the main program. And we check if n is equal to 0, for example, we're working out the factorial of 0, then the answer will be 1, because factorial of 0 is equal to 1. Otherwise, the answer is n, which is the original number, 3 for example, times the factorial of n minus 1, because 3 minus 1 will be factorial 2. Now, this is where you are using recursion, because now you're calling the same function that you're writing inside the function itself. This is called the general case. If n is 3, then the answer is 3 times factorial 3 minus 1, which is 2. So you call factorial again. Is n equal to 0? No, it's not. Therefore, the answer for that call is 2 times factorial of 2 minus 1, which is 1. So we're going to go back again and call the function. Is n equals 0? No, it's not. So the answer is 1 times factorial of 1 minus 1, which is 0. So we go back out again and call the function once more. Is the factorial 0? Yes, it is. Now you give the answer as 1. But this 1 isn't passed back to the main program. It's passed back to the previous call of the function. So you go back, previous call, so now 1 times 1. And that gives you the answer of 1 again. Then this is passed back the next level, where you say, well, 2 times factorial of 1, well, that's 2 times 1 is 2. Pass that on to the next level. So 3 times factorial of 2, that's 3 times 2, which gives you 6. That's the last stage, and we pass this one back to the main program. So instead of using iteration, where we could do the same thing by iterating a loop, we can quite simply use the same function to call itself and remember the values that it contained and work out the solution much more elegantly. Now there's some parts to a recursive routine that you need to remember. The first one is called the general case. This is where the function is calling itself. And then there is the exit condition or the base case, which is where you draw the line and say, well, okay, this is the last step of this recursive call. Because think about what could happen. For example, if we don't have this exit condition, then we'll constantly go n minus 1, n minus 1, n minus 1 forever. And that's an infinite loop. To avoid that, we need to have an exit condition, which is called the base case. And the base case will normally work with a test. In this case, if n is equal to 0, that part is checked for the exit condition. So when we're writing a recursive subroutine, there are 3 main rules to observe. A recursive subroutine must have a base case. It must have a general case. After a finite number of calls to itself, you should be able to reach the base case. If you can't reach the base case, then you're going to get trapped into an infinite loop, and that's going to be quite a problem. Now, for most problems, especially like factorial, you can do it both recursively and iteratively. On screen, you have two versions of pseudocode, so do pause the video and study these. Now, using a trace table, we can actually see how the recursive algorithm works. And chances are that in the exam, especially the paper 3 exam, you might be asked to trace a recursive algorithm out. Now, do remember, the only way out of a recursive algorithm is reaching the base case. And the steps before that are known as the winding process. So when we're looking at our factorial 3, the number is 3. The first call is 3 times factorial of 2, which is n minus 1, which is 3 minus 1. But we don't return anything because we need to work out factorial 2 first. So the second call is factorial 2, which then becomes 2 times factorial of 1. Same process, we wind it up further. Call number 3, factorial of 1. Answer is 1 times factorial of 0. We wind it once more to the fourth call, which is factorial of 0. And we know the answer to factorial of 0 because that is our exit condition or base case, and the answer to that is 1. And then we start feeding this answer back, or returning the answer back. So 1 goes into call 3, which now becomes 1 times 1, and that's returned to call 2, which is 2 times 1, which is 2, and that's returned to call 1, which now becomes 3 times 2, and that returns the answer 6 to the main program. Now visually, if you wanted to look at that, we are basically creating a stack. So the first program statement in our n is equal to 3 factorial program is to be executed is line 160. The actual parameter n has the value 3. So when the first call is made, n is equal to 3. So if you look on the stack in line 2, 160, 080 is now the address where we are going to store 3. That makes the second call, and then we have another frame on top of that which is pushed in, 082. We then push another frame in later, 081, and when the fourth call is made when n is equal to 0, that's when we reach the base case. And we push this result back onto the stack. We return to call 3. That 1 times 1 gives us 1, which is pushed back into the stack. Then we pop the results and stack frame once again and push the new result, which is 1 times 2. 2 is returned to the stack or pushed back into the stack. And then finally we have 2 times 3, and the result is pushed back into the stack, which gets us back to line 160 with the result 6. Now that's all well and good, but how do you actually code it in Python? So if you pause the video, you can go through a bit of Python code. It's pretty straightforward. We create a definition factorial where we take a parameter which is a number, and if this number equals 0, then the exit condition is 1. Otherwise, answer is number times factorial, number minus 1. And at the end, you return the answer. So it's going to keep calling itself until it reaches the base condition, number equals 0, and then it will output 1, which goes back up the chain through the unwinding part of the recursion, and in the end, you will print an output. So print factorial 0 basically should give you the base condition out. The answer should be 1. Print factorial 5 should be 5 times 4 times 3 times 2 times 1. Do code this and do have a look at what the outputs are. Now we know what the benefit of recursion is. It's just very efficient. It's an elegant use of code. However, it does have some disadvantages as well, which you need to be aware of. And these are that if you have a faulty recursive function, for example, you don't specify the base condition or the exit condition, you would rapidly run out of memory or result in a stack overflow, which causes the computer to crash. It can be very difficult to debug as it can fail many levels deep into the recursion. Currently, we just have been messing around with just factorials, which is a simple calculation, but you might be using recursion on a complex function, and tracing it out can become a bit of a challenge. And that's because it makes heavy use of the stack. Stack basically means the memory, which is a very limited resource compared to normal memory. The other possibility is that the processor time could be very high. Say, for example, if we decide to do a factorial of 1 billion, that's going to require some complex processing time, and the computer is just going to be busy with just winding and then unwinding that many levels of calculations. Quite significant disadvantages are there, so you really need to think whether recursion is an effective use of your time. easier to code, effective to code, elegant to code, but has a significant impact on computer resources. So when to use recursion? Well, basically when you have a list and you have to start at either the head or the tail and then recursively traverse the list, perhaps using pointers, that would be a good start. So whenever you're using binary trees or linked lists, recursion is often a recurrent theme there. Recursions are generally used when you satisfy the following conditions. And we touched on these earlier. You have a problem which is naturally recursive. The task must be indefinitely repetitive, and at every round, the same decision set must be applicable. If the calculations have to change, then perhaps iteration would be a better approach. And finally, you can guarantee that you won't overflow the stack memory or have a significant impact on the computer's resources. So how does the compiler actually implement recursion? Well, quite clearly, it needs to use the stack. So a compiler then uses the stack to produce object code that pushes return addresses and values of local variables onto the stack with each recursive call. So if you remember that diagram of line 160, and then we push address 80 with the values of the stack on top of it a number of times, that's how it operates. The object code then pops the return addresses and values off the stack and often pushes the results back in. Some optimizing compilers will change a recursive subroutine to an actual iterative one when producing object code to save memory, because it knows that, well, recursion is like iteration in a way. It will optimize the code and just try to use iteration instead of recursion to save the use of the stack and use RAM instead. And that's a clever way of getting around that problem of stack overflow. So to summarize, a recursive subroutine is defined in terms of itself. A recursive subroutine must have a base case and a general case. A recursive subroutine must reach the base case after a finite number of calls to itself. Each time a subroutine is called, a stack frame is pushed onto the stack. The stack frame consists of the return address and the values of all the local variables. When a subroutine completes, the corresponding stack frame is popped off the stack and the results are pushed back. Now, if you're looking for some examples of how recursion works, on screen you see another example of how a function which calculates the compound interest, not simple interest, but compound interest, works using recursion. So do pause the video and go through this. Hopefully you can identify the base case and the general case and where the recursive call is actually being made. So do pause the video and try to trace this out before continuing. You may use the values for the principal as 100 and the interest rate would be 5%. So 1.05, for example, would be the value of the interest rate. And the time period could be 3 years as a starting point. Hopefully you got something like this as an example of your trace table. So do check it, and if you missed something, obviously go back and have a detailed look at the compound interest algorithm. That's the end of today's session. Hopefully you now understand what recursion is and what the difference is between a base and a general case. Hopefully you can also trace a recursive algorithm and you understand the winding and unwinding states and how a stack frame is used to ensure that recursive calls are stacked on top of each other until you reach that base case. Finally, how a compiler deals with recursion is also crucial to your learning, and hopefully this lesson made that clear. As usual, if you do have any questions, please do get back to me. Otherwise, I'll see you in the next one.